Okay, then I will start today's class. Welcome everyone. My name is Rohan Jadhav, and this is the third session for the Polymer Reaction Engineering. So this is an interactive live session where we'll be solving a few problems which will be helpful for you to solve your assignment. So the first problem is cooling rate affects the crystalline nature of polymers. So it's a true or false question. So in the last class also we discussed something about the modulus and temperature and what are the different zones involved in a polymer structure with respect to the temperature rise and fall. So we can see here that there is a representation of the amorphous and crystalline zones present and the modulus and the temperature right here. So I'll just go through this diagram once again. So the stiffness or the modulus of a material, that is our polymer in this case, with respect to the rise in temperature. So as we can see here in the question we have been asked about the cooling rate affecting the crystalline nature of the polymer. So if we take the cooling process, so we'll be going down the temperature scale. So we will be reversing back from viscous flow to rubbery state to glass transition to the glassy state. So you can see right here that as temperature increases, definitely the amorphous regions inside a polymeric material will increase and the crystalline zones will reduce. And because of this reduction in the crystalline zones, the polymer starts to flow. You can clearly see that there is quite free space between the polymeric chains right here. And this is called the free volume of a polymer. So when the temperature rises, the amorphous zones will slide past each other and allow for the polymer to flow easily. So that initiates the viscous flow. So whenever we are cooling the system, polymer system, a polymer melt, what happens is the cooling rate will affect the crystalline nature. In what way? I'll tell you. When we are doing the cooling at a very fast rate, what will happen is the amorphous regions of the polymers does not get enough time to set back into a crystalline form. So you can see that how these small crystalline patterns are arranged here. You can see that there are in this crystalline pattern, if you can see right here, there are three zones which are perfectly ordered. The single zone in this is called a lamella. One lamella and stacking of these lamella forms the entire crystal network inside the polymer. So the individual amorphous chains which are present in the open manner like this, when you cool it down suddenly, they are restricted in their movement and they don't set back into this crystalline lamella. They are just present in a haphazard manner in this network. So you can see that they will be just frozen like that as they cool down. So sudden cooling down will just keep the material frozen like this, and the free volume inside the material will be very high. And because of this, the material is extremely brittle in the sense like it cannot take on any load and it is very inflexible and it will break easily. Whereas when your cooling rate is slow enough, the individual amorphous regions of these chains they will slowly compose back together to form these crystalline lamella. And once these lamellas are stacked upon each other, they will form structures called spherulites. These spherulites are responsible for giving the crystalline nature to a polymer. So when the cooling rate is very slow, but the crystalline nature of the polymer comes out in the best way. and the glassy state achieved is having much higher modulus than the one with the faster cooling. So that's why whenever polymer processing is being done, when we are handling the polymer melt, in that case, what happens is we always try to cool the polymer at a very slow cooling. That usually happens in the compression molding process. We have a molten polymer, and when we give it some shape, we allow the cooling time to be higher so that the crystallinity achieved in that cooled product is much higher than the initial, since we are changing the shape of the material. So yes, cooling rate affects the crystalline nature of the polymer. It's true. Next question. How does tacticity affect the properties of the polymer? Now, first of all, let's know what is tacticity. Tacticity is the uh, like tacticity. The word itself means arrangement. Arrangement of how the what is the tactile arrangement of the polymer materials. Now, here I have three examples right here. You can see that you have a polymer backbone chain in the middle in all of them, and you can see the arrangement of the M and R groups, how they're present. You can see right here that the C C double bond O and O minus are in the first atactic polymer. They both are arranged on this side, and the other group is arranged on one side on the alternate, and the again on the alternate side. So there is no definite arrangement in this. When the functional groups are present without any definite arrangement on either side of the polymer backbone, it is called the atactic polymer. Next, we come to the syndiotactic polymer. In syndiotactic polymer, what happens is you can see that the C double bond O minus groups are arranged in the exactly alternating fashion. One is on the left, other is on the right, left, right, left. We can clearly see it's arranged in that way. And this is called the syndiotactic polymer. Next, we come to the isotactic polymer. In isotactic polymer, all the functional groups are present on a single side. So from this itself, you will have some estimate about how the properties of these polymers are going to differ. For example, if you were to take the eutectic polymer, what will happen in this case is that the melting point of the atactic polymer will be much lower than the syndiotactic and the isotactic polymers. In many cases, what happens is syndiotactic polymers are the best suited and the one with the highest mechanical strength and chemical resistance other than the isotactic and the atactic polymers. So the order goes from syndiotactic, isotactic, and the atactic. Why does that happen is because of the alternating arrangement of the functional groups. This gives it a steric hindrance stability. Why? Because when the groups are present at the one side, the charge distribution is unequal, and because of that, there can be steric hindrances. But in this case, you can see that since the functional groups are present at far away distance on the alternate side of the polymer backbone, the steric hindrances are managed properly. And because of this, the what is the resultant effect is that much better closer packing can be observed in syndiotactic polymers. So the packing density will be much higher in syndiotactic, that followed by the isotactic, and that followed by the atactic polymer. In isotactic polymer again, we can see that since all the functional groups are present on one side, the charge distribution is present in such a way that one side is open or deficient to charge, and one side is having the higher charge. So it will create an entire dipole present in the backbone of the polymer chain. Okay. So here again, the secondary forces will be much more active in isotactic polymers. And in syntactic polymers, the packing density of the polymer chain itself will be much higher, providing it very much higher properties. So how does plasticity affect the properties of polymer? Density changes will be higher. Density changes will be quite significant. Then makes the chain more flexible. It depends what kind of plasticity you're going for. Reduces the steric hindrances. That is true. and we can clearly see it in symbiotic polymer versus the atactic polymer or none of the above. So here we can see density change is true, reducing the steric hindrance is true, and making the chain more flexible is also.
Sir, is it a way that we should take all the three? It is
What's it?
whether we should say all the three are like applicable and which one is more prominent.
Yeah, that is another thing that 1 second, sir, just 1 second. The thing is, while manufacturing of polymer production, it is actually favored that we get the symbiotic polymers for the production because atactic polymers are basically having very low properties. So either symbiotic or isotactic. So while manufacturing process itself, the different catalysts which are used to facilitate the polymerization reaction can decide what kind of tacticity the polymer will have. So that's why we always try to go for either symbio or isotactic polymers. Similarly, the polymer polypropylene, its isotactic properties are sometimes much better than the symbiotic properties because the functional groups which are present on the polymer backbone, the way it is arranged will also provide different kind of orientation through which the property changes. So, as your question said, it is more favorable to have symbiotic and isotactic, but not all polymer chains are equal, like I said in the previous class. So we will have some chains which will have atactic orientation also. But we always try to keep the symbio and isotactic polymer percentage much higher to get much better properties in our polymer. Moving on to the next question.
Sir, one small doubt actually is with respect to the answer, whether
Yeah.
we it's like either we are looking for only one or all three, like
No,
this
no, we
question.
are, yeah, okay. We are actually looking for only one of them. Like the best one is the symbiotic. So we are trying to look for that itself.
No, sir, not that, but is changes. Like question says that how does staticity affect the properties of polymer?
Oh, okay. Yeah, what we are saying is density change is correct. Then reduction of the steric hindrance is correct. And these two are only correct. Making the chain more flexible is a subjective answer. It can either occur in any one of them. So it depends on the polymer. So 1 and 3 are the correct answer.
Okay.
Hmm. So moving on, we have one question from the chemical kinetics. The rate of reaction is the function of which of the following actions? Now, first, I think in the polymer reaction course itself, you might have come across now the chemical kinetics, since this is the third or fourth week. So I think Sir must have already introduced about the chemical kinetics and what are the kinetics of the reaction. So from the rate of a reaction, from that itself, you can tell that how fast or how slow a reaction is proceeding. So which of the rate of reaction is the function of which of the following options? So first we have the reacting material, temperature, concentration, and type of reactant. So in this, the first one is the reacting material. Now, the reacting material itself what does that mean is the reacting material itself is composed of the material which is quite spontaneous in nature, or it can have very high free energy. That is, it gives free energy because of which it can spontaneously undergo reaction. So the inherent material itself affects the rate of the reaction. So this is the correct one. Next, we have the temperature. The temperature at which the reaction occurs. How can that be defined is that if you are trying to ignite something or if you are trying to make something evaporate, the more you increase the temperature, the faster the reaction happens. Or in some other cases also, the more increase in temperature will give you a faster kinetics or the rate of the reaction. So reacting material and temperature are correct. And next comes the concentration. Now, how can concentration of the reactant affect the rate of the reaction is if the reactants are present in abundance, then the reaction order is quite stabilized and it occurs in a stabilized manner. So one example of that will be photosynthesis, in which we have the sunlight coming on top of the leaves, and then that is exactly producing the glucose. And in that case, the abundance of the reactant is present in a high amount. So that is following a zero order reaction. Why? Because in that case, the concentration dependency is like quite less. And you can see that the rate of the reaction, as we go to the next orders, that is the zero, then to the first, and then to the second, the concentration of the reactant change affects the rate of the reaction a lot. Then we have the type of reactor used. Type of reactor used defines what will be the yield of the reaction itself. So if you want to maximize the product and the order of the reaction, then you will know with respect to that what kind of reactor is to be used. And there are different types of reactors, such as batch reactors, then semi-batch reactors, and then continuous reactors. And the name meaning from the batch, semi-batch, and the continuous is that the way the reactants are put into the reactor. Like in a batch process, if you are trying to create a certain batch of the product of, let's say, 10 kg, so you're going to put in a certain amount of the reactant, let the reaction happen, and then obtain the product. So that is for a batch. And in semi-batch, you're going to put some products in, some reactants inside the reactor, and then either a catalyst or some other stream of inert or some other material is being fed continuously. So that there is a like a clear demarcation between the continuous and the batch process. So that's why, since they are both combined there, it is called a semi-batch reactor. And in the continuous reactors, what happens is the constant stream of reactants is being fed inside the reactor to form the product on the other side. And most of the industries use the continuous type reactors. So where we are obtaining the uh, products in a continuous manner. So the rate of reaction is dependent on the reacting material, temperature, and concentration. The first thing. Next one. What is the slope of the plot of natural logarithm k
So it is,
versus?
sorry, just to clarify.
Yes,
So
sir.
I think it is all the three, right? Like the
Yeah, yeah,
reactant,
all the
and
three. Yes, yes, all the three.
okay,
Yeah.
right.
So next question is, what is the slope of the plot of ln k, that is the natural logarithm k, versus 1 by t for a reaction where the activation energy E is positive for temperature dependency of the reaction rate constant given by the Arrhenius equation. So first on the left hand side, we can see there is a diagram where on the x-axis we have the fraction of molecules with a particular kinetic energy E and the reaction coordinate, how it is moving, with respect to the energy on the y-axis. So you can see that the purple line here, it's showing how the reactant goes, how the reactant starts from a much lower activation energy, and then it reaches to a high where the maximum activation energy is achieved and it forms the activated complex. Now, what is this activated complex is that the energy levels of the reactant and the product are quite different. For example, you have two reactants, they won't react by themselves automatically. You have to either provide some catalyst, some surface, or some kind of input, that is the temperature, for both of them to react. So, for example, if you provide both of them a temperature, certain temperature, they both will react and form a complex, intermediate complex. Intermediate complex is something which is formed between the reactant and the product. And this activated or the intermediate complex is nothing but it is a complex which is not in its final form. Final form in the sense like it might either have some incomplete reaction going on or it is at a higher energy state. And once that higher energy state loses some of its energy, it reaches a much more stable form that forms the product right here. So you can see right here uh, that the 500 Kelvin and 300 Kelvin, you can see that the activation energy required for the 500 Kelvin is much lesser than the 300 Kelvin. And that's the reason why the reactant is how the reaction coordinate moves is the reactant forming to the activated complex, and then it gives the product. So the amount of energy required for the 300 Kelvin process is much higher than the 500 Kelvin. So you can clearly see that the 500 Kelvin process requires lesser energy since the temperature itself is providing sufficient activation energy for the process. So that is this. So the question asks us that the rate of the reaction in this case, how will it differ? So we have two different temperatures here. So if I take the graph for 1 by T, that will be 1 by 300 and 1 by 500. Let's come on to the right hand side. So we can see that the reciprocal of 1 by 500 will be much more smaller than the 1 by 300. So let's say that 1 by 500 will be present somewhere here and 1 by 300 will be in front of it. So if we were to draw the curve of the rate of reaction at 500 Kelvin, that will be 1 by 500. The slope of the line will be much more sharper than at the 1 by 300 Kelvin. So 1 by 300 Kelvin will be present in a much more slighter slope. So 1 by 500 will be present here and 1 by 300 will be present here. And the reaction slope will be something like this for the 1 by 500 one and for 1 by 300. It will be something like that. So the slow form will be much more gentler than the one at the 500 Kelvin. And this one will give us the activation energy by the gas constant slope. This slope is related in that manner. So the slope of the plot of ln k versus 1 by t for a reaction where the activation energy is positive for temperature dependency of reaction rate constant is given by the Arrhenius equation is like this, that the correct answer is minus E by R. Since the curve is going down, you can clearly see that it is having a negative slope. So that will be given by minus E by R. And this is following the Arrhenius rate equation. And you might have already come across the Arrhenius law for different temperatures and how the relationship is changing with the natural logarithm for different reaction rates at different temperature. So I will just write down here. So that will be given by ln k2 by k1, uh, which will be equivalent to the uh, the ratio of the activation energy by the gas constant, which is present here in this. So we have the gas constant here, E by R, and multiplied by the changes in temperature reciprocal, as shown in the graph right here. That will be 1 by T, 1 by T1 minus 1 by T. So this relation itself tells us that the slope for this expression will be negative E by R. So from this expression, we can clearly define the Arrhenius equation, and the answer for this question is minus E by R.
So just a doubt, a clarification whether
Yeah,
negative we have to take as a slope like one inverse of temperature is there in x-axis. Okay,
yeah,
anyway, it is going coming down. That is correct.
hmm,
So it is minus E by R.
yeah,
Okay.
yeah. Next we have the
So,
which one?
sir, what would be the correct answer, sir?
Yeah,
Minus E
the
by R.
yeah, minus E. Okay, yeah, because already the yeah y-axis is present in ln k, and we have 1 by temperature right here. So according to this expression right here, you can treat it like this. So if we have y is equal to mx, oh yeah, sorry, here it will be negative. So then again, you will have minus E by R as your slope.
Okay.
Yeah. Next we have, which of the following statements is wrong for the non-elementary reaction systems? So first of all, I will define what is a non-elementary reaction system. Elementary reactions occur when your reaction is quite straightforward, like when A plus B is given C, like quite a straightforward reaction. It will have only one activated complex formation, and then it will just proceed down to the products. So again, here we can see that there is a reaction progression graph and there is an activation energy or energy graph. So you can see that how the coordinates are moving. It starts with the reaction, the black curve I'm talking about, the elementary reaction. It will rise to the activated zone, and then from there onwards, it comes down to the product side. So here, this reaction is occurring without catalyst. I mean, you can ignore the part of the catalyst itself because it can either happen with or without catalyst. That is a different thing, but that will be your elementary reaction. In non-elementary reaction, what happens is that your reaction proceeds with formation of multiple intermediate complexes. You can see that 1, 2, 3, and 4. You can see that there are 4 types of different intermediate complexes which are being formed, and that then proceeds to form the product itself right here. So there are 4 different, like not, this is just a general example. There are many times more than 4 intermediates being formed. There are many, much more intermediates being formed. And most of the reactions which are happening in nature or polymer reactions which we are trying to study actually form, actually are quite complex reactions. And they do not proceed as elementary reactions, uh, which are shown in normal examples. So usually, there is no direct relationship between the rate expression and the stoichiometry of the reactants involved in the medium because there are many intermediate products being formed. So that's why it is very difficult to establish a direct relation between the expression itself and the stoichiometry and the powers to which these stoichiometric coefficients are raised. So that's why the first one is actually correct statement. So this is the correct statement, but this is not the answer for our question. Why? Because it is telling us to state the wrong term for the non-elementary reaction system. So this is not the right answer for this one. Let's go to the second statement. The stoichiometric coefficients are same as the power raised to the corresponding reactant concentration terms used in the rate law. Then the reaction is said to be non-elementary. Now, this statement, we can clearly see that it is saying that stoichiometric coefficients are same as the power raised to the corresponding reactant concentration terms. Just now we talked about how the complex reaction or the non-elementary reaction proceeds with the formation of much more intermediate complexes than the normal elementary reaction. So the coefficients to which your stoichiometric terms are the stoichiometric coefficients to which the concentration terms are raised is not equal is not the same as the corresponding reactant concentration. So this statement is false, which tells us that this will be the one of the answers for this question because this is not pertaining to the non-elementary reaction itself. The third one is there are needs of a series of elementary reactions to solve a non-elementary reaction system. Now let's analyze this thing. In this complex reaction, the red curve, you can treat the first bump itself as an elementary reaction. Can we do that? Yes, we can do that. What is happening here is we are starting with the reactant, then we have our first rise, and then we stop at this point. If we treat this single bump as an elementary reaction, we can break down the entire complex or the non-elementary reaction into series of elementary reactions. This will be the first one, next is the second, then third, then fourth, and finally we are led to the product. So to make our calculations more simpler, we can break down the entire complex reaction into small elementary pieces. So that's why there are needs of a series of elementary reaction solve a non-elementary reaction systems correct is the correct term, but not the answer for our question because we have been asked to choose the wrong ones. Next, we have to assume a series of elementary reaction occurring with negligible amount of intermediate product formed for a short period of time. Again, this is the correct. This is just synonymous to the previous statement. Why? Because the amount of intermediate product formed is only present for a small period of time. So here there are four stages where the products will be formed. One, two, three, and four. So there are four stages here where the products will be formed, and that's why we have to assume a series of elementary reaction occurring with the negligible amount of product. So again, this statement is true and not the right answer for this one. So the correct answer for this question is only the second statement, where the stoichiometric coefficients are same as power raised to the corresponding reactant concentration. So this is the right answer. Moving on, choose the correct option from following statement. In the Arrhenius law, the reaction rate constant is directly proportional to the temperature. Next we have in collision theory, the reaction rate constant is directly proportional to the square root of the temperature term. And next we have the in transition state theory, the reaction rate constant is directly proportional to temperature term, and the collision theory is based on the kinetic theory of gases. So we will go from the first statement. In the Arrhenius law, the reaction rate constant is directly proportional to the temperature. So let's take a look at this example right here. So you can see that the rate constant here involved is the K2 or K1, uh, and they are often like they are directly proportional to the temperature. As in, when the temperature increases, the rate constant will also increase. Because we are having you can see right here that as the temperature increases, the slope of the curve also increases. So in that case, in Arrhenius law, when the temperature is higher, the rate constant will be much more higher and the reaction will proceed much more faster. Next, we have in the collision theory, the reaction rate constant is directly proportional to the square root of the temperature term. So here we have been shown that the collision theory says that the again these collision theory and Arrhenius law all are coming from the similar theory that is based on the kinetic theory of gases, which leads me to the fourth statement of the problem right here, that collision theory is based on the kinetic theory of gases. So what it says is that the higher the number of collisions, the higher the reaction rate will be. And that will happen when your temperature is higher. Why? Because at high temperature, the molecules are having more energy to collide with each other. And the more they collide with each other, the more reaction rate constant will be higher. So that's why the square root of temperature term is not it is actually collision rate theory. Reaction rate constant is directly proportional to the square root of the temperature term. It this statement is not the correct one because it is directly proportional to the temperature itself. So it is proportional with some proportionality constant present. So the reaction rate constant is proportional to the temperature term. Next, we have the in transition state theory, the reaction rate constant is directly proportional to the temperature term. Again, in transition state theory, and what happens in transition state theory is that the reactants transition to a higher activated state, again shown in the previous problem right here, that reactants come together to form an activated complex to reach a higher activation state, and from then onwards, they will drop down again to the product state. So the reaction rate constant is directly proportional to the temperature. So as the temperature is higher, the movement to the energy required for reaching the intermediate stage or the transition state is much lower. So that is also the correct. So 1, 2, 1, 3, and 4 will be the correct answer for this question. Next, is the which of the following statements is incorrect for the order of the reactions.
So
Uh,
one doubt in the earlier query.
yeah, yeah,
So here actually, though we are telling collision theory, the rate equation when we write
yeah.
in terms of like temperature, square root of temperature, then when we convert it into logarithmic terms, it is converting into normal.
Normal.
So that
Okay.
okay, so that way we cannot consider this as directly proportional to square root. That is the point.
Yeah,
Na?
yeah, yeah. That is
Okay,
yes.
same
Yeah,
same as the case. Transition theory anyway, it is directly proportional, and Arrhenius law also okay. Yeah,
yeah, yeah.
that is
Correct.
not itself we have seen. Though it is inverse of temperature, like temperature is inverse. Higher the temperature, the rate constant will be higher.
Ah, yeah.
So it
Yes.
is directly proportional. Yeah.
Hmm.
Okay, clear.
Yeah. Next, we have the which of the following statements is incorrect for the order of reactions. The overall order of reaction can be fractional or a whole number. First statement. Second, we have the sum of power raised to the concentration terms and rate law is said to be the order of reaction. Then we have it can be defined for elementary and non-elementary reaction system. And third, the order of reaction and molecularity are always same for a reaction system. Okay. So we will analyze them one by one. The overall order of the reaction can be fraction or whole number. Now, what does this mean is that the again the basic definition for order of the reaction is that the sum of the powers raised and the concentration terms are raised to. Now that depends on the stoichiometry of the entire process. So the overall order of the reaction can be either fractional or a whole. It can be fractional and it can also be a whole number. Why? How it can be fractional is that sometimes the reaction stoichiometry, if you would have seen, sometimes it involves the fractional values also, just to balance out the reactant size and the product size. So in that case, the fractional coefficients which are present in the stoichiometric reaction can be raised to the concentration powers, and because of that, the overall order of the reaction can be fractional or a whole number. Most of the time, it is a whole number, but for some non-elementary reactions and complex reactions, it is present as fractional. Next one we have the sum of power raised to the concentration terms in the rate law is said to be the order of the reaction. This is the straightforward definition of the order of reaction. So this is also correct. So the first two statements are correct and they are not the answer for this question because we have been asked to find the incorrect one. Next we have it can be defined for elementary and non-elementary reaction systems. Again, if you break down the non-elementary reaction system into set of elementary reaction systems, and then some of we can like sum or bring them together, you can still define the order of the reaction for a non-elementary reaction system also, because it can be easily defined for elementary reactions, but it can also be defined for non-elementary reactions if you divide the non-elementary reaction system into different parts of the elementary reaction system. So this statement is also correct. The last one is the order of reaction and molecularity are always same for a reaction system. Now, what does the order of reaction and molecularity? Order of reaction is the sum of power raised to the concentration terms in rate. But molecularity means the number of molecules which are colliding to form the product or to facilitate the reaction to form the product. These two quantities cannot be same. Why? Because in molecularity, the number of molecules which are colliding together can be different, and the molecules which are colliding, which form the activated complex, are different. So it is more like that hundreds of collisions are happening at the same time, but only few of them will succeed, and then they will move on to form the activated complex, and which will give you the molecularity. And that is the exact reason why any of the reaction cannot 100% like give you the product. 100% conversion in the sense like 100% conversion of the reactant to the product is sometimes not possible. And we have sometimes leftover reactant because the molecularity is never the same as the order of the reaction. So that's why this statement is incorrect. Are always same for the reaction system. They can be same in some cases and they are different in most of the cases, but order of the reaction and molecularity cannot be equated as same for reaction systems. So this is the incorrect statement in all of them. Moving on, a certain first order reaction is half completed in 30 minutes. The rate constant for the reaction must be. So we have been given four options. Here I have added a picture right here which is describing the half-life of reactions. Now what is the half-life of a reaction? Whenever as I said in the previous one also, sometimes what happens is that the 100% conversion of reactant to product is not possible in most of the reactions. So what happens is when you have a set amount of reactant present and when it is consumed 50%, exactly 50%, the amount of time it took to consume this 50% of the reactant will give you the half-life of a reaction. Now we already know that there are different orders of reaction. First we have the zero order, then we have first order, and then we have the second order. So we can see that there are different half-life times present here for different orders of the reaction. So in zero order, what happens is it is directly proportional to the concentration. So you can clearly see that T half is equal to concentration divided by twice the rate constant. So larger the concentration, initial concentration, larger is the half-life. So as I said in the previous example, previous to previous example, that the order of the reaction, zero order reaction is abundantly uh, related to its concentration. So when the initial concentration is higher, your T half will also be very much higher. Then we come to the first order reaction that T half is equal to 0.693 by K, and it does not depend on the concentration term itself. So it is only a function of the inverse function of the rate constant. So you can see
Sir,
how
is the
the
reactant, right?
A naught. A naught is the reactant. And the naught represents the initial concentration.
Zero order.
Yeah,
Initial one, okay.
yeah,
Initial one.
yeah. So T half does not depend on the uh, A naught. So first order reaction half-life is not at all dependent on the concentration of. Okay. Next we have the second order reaction. Here we can see that T half is equal to 1 by K multiplied by the initial concentration of the reactant. So when the concentration of the reactant increases, your T half is going to decrease. Why? Because second order curve, if you were to plot the second order curve of a reaction, it is going down at a very high rate. Like the drop and the slope of the second order reaction is very high. And because of that, if we were to put in more initial concentration, the consumption of that reactant will happen much more quicker than first order and the zero order. That's why second order is inversely dependent on the second order half-life is inversely dependent on the initial concentration of the reactant. So here in the question we have been clearly given that it's a first order reaction and it is half completed. So we have the T half given to us already, that is 30 minutes. So you substitute the 30 right here and 0.693 is already present. You can clearly perform some arithmetic and get the value for K. You can bring the K up, bring the 30 minutes down, and you can divide these two. And the correct answer for this, I will tell you right now, is 0.0231 minute inverse. Why minute inverse? Because when the K goes up and T half comes down, it becomes the minute inverse. So 0.0231 minute inverse. One way to tell the answer again is that if you know the expression for this itself, you can see that T half comes down and it becomes minute inverse. And in the question itself, the unit has been given in minutes, and rest all uh, units are in minute, R inverse, and second inverse. So you can clearly see that 0.0231 minute inverse is the correct answer for this question. Uh, Moving on to the
Sir,
next question.
sir, can I ask one basic question, sir?
Yeah, yeah.
Sir, I just want to know, ki suppose if it is like first order or second order or zero order,
Hmm.
how practically we can understand ki whether it's a first order or second order? How we will understand it's a first order or second order? By just
Okay.
by taking the power of that one, matlab, that is like practically how we can understand.
Hmm. Okay. Uh, let's go to the next question, and in that, I think you will understand. So we come here. Okay. So here we have been given the concentration versus the rate on the graph right here. And then next we have the time versus the concentration graph or the 1 by A graph. So whenever you want to practically define the order of a reaction, right, we only have two parameters and two parameters only. That is concentration and time. So whenever you are trying to map any kind of reaction rate or any data like that, it is always concentration and time. So the best way to visualize it is that when you have the concentration present in in very high amount, it will always give you a zero order reaction. Why? Because zero order reactions are always dependent on the initial concentration of your reaction. Okay. And for the first order reaction, the decline slope will always be constant and negative slope will be there. So it will be decreasing in a downward slope. The only way to tell what kind of order of reaction it is you have to first get this expression. You can see right here on the right hand side. This expression is for the second order reaction. But of course, you might also know the expressions for the first order reaction and the zero order reaction. So what you do is you fit these equations to your curve. You try to fit it to your curve of concentration versus time. Then you will see that the curve, the data which is exactly following that equation will give you the correct answer for what order of reaction it is for. Okay, so here you can clearly imagine that uh, just imagine this expression which is present here as y is equal to mx plus t. That is the equation for a line. So you can see that we have this term as 1 by square bracket a as y is equal to mx, that is k multiplied by t, plus c, that is 1 by a naught. Why 1 by a naught is constant? Because we are starting with the initial concentration. So that is the square bracket a naught. That will be your initial concentration. For example, you have some decomposition reaction going on in your laboratory. What you do is you measure the initial concentration of that reaction, initial concentration of the reactant, and that will be your a naught. So you will have some value for 1 by a naught. Now, as the reaction proceeds, you will only have two data points. That is square bracket A, you can monitor that, and then T, you will have T. So since you have all these parameters, you will be able to find out K, and the K will be given by the slope. So that's why you uh, plot the time versus the concentration, and when it follows exactly the equation of the first order, second order, or third order, or the zero order, you can clearly tell that what kind of order of reaction is occurring. And this is possible for all the uh, everyday chemical reactions. So that's how you can tell easily what kind of order is being followed by your uh, reaction process. Okay, I hope I was able to tell you that uh, tell you the explanation for that, how to physically signify what kind of what does the reaction order mean. It just means that the speed at which the reaction is proceeding is much more higher. That is the exact reason.
Uh,
Yeah.
was that like based on order?
Hmm.
What would be the significance? Suppose it's a zero order reaction. Suppose, sir.
Hmm. Hmm. Hmm.
So, what would be the significance that it is a zero order, so reaction will be like that, or if it is like first order, the reaction will be like that. So, how to understand that? Suppose there is a
Hmm.
simple equation, like you said, sir. Suppose there is a decomposition reaction.
Yeah.
So, whether it can be zero order and first order at the same time, or based on what we can decide is the first order or second order, or only simply looking at the reaction we are writing, we are getting is the first order or second order or third order.
Actually, that's a very good question. See, for that, we need to again come back to the elementary and non-elementary concept. So, like you just said, that suppose we have a reaction, can it be either both orders? No. When you can see here the complex reaction, when you are seeing the first bump right here, right? Maybe this bump is following the zero order kinetics, and maybe the next bump will be following the first order kinetics. So, yes, it can happen. Initially, when the concentration is reducing with respect to time, the initial period where the concentration drastically reduces, that might be following the first order reaction. Okay. And after that, if it starts becoming constant, maybe that portion is following the zero order. Okay. So in real life or in the real reactions, there can be demarcation between the regions where the reaction is behaving in a certain order. And it can happen, and it has happened. Uh, Even I am working on something called like degradation studies of a particular material. I cannot disclose it right now, but I'm working on that, and I have seen that the order of the reaction and the concentration versus time relation is changing as the time passes. So my time period for which I am studying is around 20 to 30 days, and in that, the reaction order and the way the curve is changing for time versus concentration is changing continuously. So that is a clear sign of a complex reaction. And you can see that the order of the reaction is also changing with respect to the concentration which is available for the decomposition or the degradation. So as you are saying, the significance is that whenever the reactant is present in abundance, you can say that it's a zero order. As you can see the half-life relation also, that when the larger A naught is present, your T half is again larger. And that is the exact reason why I gave you the example of photosynthesis. Photosynthesis is a natural reaction, and as long as sunlight is present for the plant, it will keep producing the product. Okay, so that's why uh, the zero order reactions are like they won't be dependent on the concentration itself because concentration is present in abundant amount, like large amount of concentration is present, and that is the exact reason the reaction keeps going on, and it will give you a constant slope. The concentration versus time, right? It is having a constant slope. Why? Because the concentration is so high that even after the formation of product, there is not much depletion, and it is following a zero order kinetics. Whereas in first order, the decline is somewhat like a slope, and in second order, it will follow some uh, exponential or sudden decline in the concentration. Okay, that's how you are like you can physically connect the reaction which you are observing in the real life or in your laboratory with respect to the changes in the equation present itself. Okay, so that's how you correlate the theory with practice. Maybe like that's how like we have also done it in our lab also.
Understood, sir. Understood,
Yeah,
sir.
yeah. So for this question again, the slope of graph in between 1 by Ca, that is 1 by concentration of A, versus time t in second order irreversible reaction with equimolar fluid concentration is. So the concentration of A is continuously, like you can see that it is increasing, and the rate here, the rate that is the dA by dt, that is the decomposition of A or the decline of A with respect to time is shown here. So this is a negative slope, and since we have equimolar field concentration, concentration of A is increasing. So for that, when we plot the graph of time t versus 1 by A, the slope is k. Slope is equal to k. When we go to solve this with the equation given right here, 1 by A is equal to 1 by A naught plus kt. So when we solve it, we have the slope given as positive k. So you can see that the reaction rate is increasing as time goes on. So the answer for this is K, the first one. And this brings us to the last question. For a zero order reaction system, the rate of reaction is always independent of. So I guess you can easily answer this question now after so much discussion that the correct answer for this is concentration, because concentration is present in such an abundant amount that the reaction itself does not worry about the reactant getting over, and that's why it is independent of the concentration. So it is independent of the concentration. So these were the questions for today's class. Uh, Maybe like you'll be able to solve uh, the other questions also for the subsequent assignments. So I think for this week, reaction systems were being taught in the class, and slight introduction about the polymer properties also. So I have covered those in this class. This lecture will be available on YouTube. So if you want to revisit for any other explanation, you can visit that again. And you can, if you want, you can ask me any doubts, or you can put them on the forum itself, and I'll be trying to clear those doubts there also.
Sir, for clearing the doubt, sir,
Yeah.
it will be only during the session, like weekly session.
Uh, like you
Like
can,
today you have explained all the questions. So
yeah,
in that forum only we have to doubts will be clear, sir.
you can actually mail me also if you want, but it will be
Okay, okay.
better
No,
that
no,
if you,
I'm just, it will be good, sir. If it's like in a forum or in kind of video, it will be more, I think, good. Like I can.
yeah, yeah. Hmm. Yeah, it's fine. Then put it on the forum. That will be much better. Okay.
Yeah, because sir, during the lectures,
Hmm.
I find something not like getting clear of some concept and all. That may
Yeah.
be a little bit of conceptual, maybe very silly. So
Yeah. Yeah.
I think, sir, because it is something which is more into depth of depth of the thing.
Hmm.
So in that case, I think asking such questions will help me getting the answer.
Yeah. Yeah. Correct. Correct. So it's fine. You can put it on the forum, or else, if you want to ask me any questions, maybe I can prepare some explanation and show it to you in the next class also, if you want.
Fine,
Okay.
sir. No issue, sir. No issue. Oh,
Yeah.
no issue.
Yeah. Okay then. So yeah, yeah, that's all. So we have discussed the 10 questions for today, and yes, that's all.
Okay, thank you very much.
Yeah. Thank you, sir. Thank you.
Thank you.
Thank you,
Bye.
sir.
Yeah.